Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over acid strength and molecular structure, but this time we're going to go over the oxyacids. So let's get into this. So again, let's remind ourselves what the question is, or the questions are. The first question is, why are some hydrogen containing molecules act as acids and others don't? Or why do some acids, why are some strong and others weak? And so in the last video we went over binary acids where you have hydrogen and one other element bonded together. So you have only two elements. In this video, we're going to go over the oxyacids. And the oxyacids are the acids that have hydrogen bonded to oxygen, and the oxygen is bonded to another atom. So here's the generic formula for an oxyacid. So you have, instead of the hydrogen being bonded directly to X, hydrogen is bonded to oxygen, which is then the oxygen is bonded to some element X. And this X could be bonded to other atoms. So that's the formula, that's the structure. And so, what are the factors affecting the ease of donating the hydrogen to another molecule like water? So, when you put it in water, what factor is influencing the ease of donating that hydrogen? And these are the two factors. Again, electronegativity of X this time. So, the electronegativity of this element bonded to the oxygen is going to be a factor. And another factor, since we're dealing with oxyacids, is the number of oxygen atoms that's bonded to X, right? So you can have oxygens bonded to X while X is also bonded to oxygen here. So those are the two factors. So let's go over both of them one at a time. So the first one is the electronegativity of X. So here we can see that we have these three different acids, these three different oxyacids, and they differ by the atom that's bonded to the oxygen. So X here is going to be iodine, and then X here is bromine, and then X here is chlorine. And so if we look at the electronegativities of these three elements here, iodine has electronegativity as 2.5. Bromine has an electronegativity of 2.8, and chlorine has an electronegativity of 3.0. And so you can see that the Ka value is increasing as the electronegativity increases. So, and this makes sense. And let's remind ourselves what the Ka value is telling us. The Ka value is telling us how easy it is to ionize. So the larger the Ka value, the more easy it is to ionize and lose that hydrogen, and therefore it's more acidic. And this makes sense because if we understand what electronegativity is the amount of pull, or how much that element wants the electrons in the bond. So if you are more electronegative, that means you're going to be pulling on those electrons more. You want them more towards you, so those electrons are going to stay around you. So iodine is going to pull not as much as chlorine. So chlorine has a higher electronegativity. So what's going to do is it's going to pull on that electron density. So the electron density is going to be pulled this way towards the chlorine, and therefore lowering the electron density around this oxygen and making this bond here weaker, and therefore it's going to be more easily removed. So you can donate this hydrogen more easily with the HO bond being bonded to chlorine versus iodine. So iodine is not as electronegative, so it's not going to be pulling on the electron density as much. So that's going to allow for the OH bond here to be greater, be a stronger bond. So that explains in way of electronegativity. So electronegativity of X will influence the ability to donate this proton. So again, higher electronegativity of this element here, then the more acidic this hydrogen becomes. Well, what about the number of oxygens bonded to the X So here we have X and we have OH here, but then what's bonded to the X? So here we're looking at number of oxygens. So here we have our 4 acids in this table. We have the perchloric acid, chloric acid, chlorous acid, and hypochlorous acid. And so you can see that the only thing they differ by is the number of oxygens. And so you can see here that with the 3 oxygens bonded to the chlorine, you have a strong Ka. So this is a strong acid. Here you have 2 oxygens bonded to chlorine, and the Ka is 1. Here you only have 1 oxygen bonded to the chlorine, and you have a Ka value of 1.1 times 10 to the negative 2. And here you have no oxygens bonded to the chlorine, and so you get 2.9 times 10 to the negative 8. So as you increase the number of oxygens bonded to your chlorine here, your atom X, the Ka value increases, and therefore the acidity is increasing. Well, why is that the case? Well, it goes back to the electronegativity of oxygen. So oxygen is rather electronegative. So the more oxygens you have, the more there's going to be pulling on the density of the chlorine. So the number of oxygens here, you have 3 oxygens. So all of these oxygens are pulling on the electron density away from the chlorine, and therefore in turn the electron density of the bond here between H and O is also going to be weakened, and that electron density is going to be pulled. That's going to increase the polarity of the bond, decrease the strength of the bond, and therefore the hydrogen is going to be more easily given off or donated to another substance like water. So you can see that this is a strong acid because you have so many oxygens bonded to it. You decrease the number of oxygens bonded to the chlorine, you're decreasing the amount of electronegativity that's pulling on the density, and so that this bond here is not going to be as weak or as polar as this bond here. So this getting rid of this hydrogen is not going to be as easy as getting rid of that one. So the Ka value is not as high. And so you can see the Ka value decreases as you decrease the number of oxygens. And so that is why when we look at, say, if we're going to compare H2SO4 with H2SO3, we can predict that based on the oxygens alone, that H2SO4 is going to be a stronger acid than H2SO3. Sorry about that. So same thing with HNO3 here. So here we have 3 oxygens bonded to the nitrogen. Here we have 2 oxygens bonded to the nitrogen. So we could predict that HNO3 is going to be a stronger acid than HNO2. And we know from before or from other videos we talked about, H2SO4 and HNO3 are strong acids, whereas these 2 are weak acids. And so that follows and meets our prediction. So I hope this video is helpful. I hope this clarifies why certain oxyacids are weaker than other oxyacids. If you enjoyed this video, if you learned something from this video, please make sure you hit that like button and also subscribe to my channel. Hit that notification bell so you can be notified by other videos I put out. Put a comment down in the comment section. Let me know what you think and if you have any questions. Thanks for joining me. Have a great day.